Okay, good. So now we're going to look at an example circuit, right? Since we kind of formalized all of this, let's go to one quick example. So the example is the well-known teleportation circuit. So the teleportation circuit does what? That's the following. For just a moment. Yeah, we can make more space as we go along. Okay, so what is the objective? The objective is that, so there's Alice and Bob. Oh, it's just Alice and Charlie. Okay, it's just for simplicity. Okay, and Alice wants to send, so they initially hold some internal state. Okay, this is register A, this is register B. And Alice is holding some state C. Yeah, okay, maybe the nomenclature is probably not the best, but okay. So Alice has some state psi, and she wants to send this register C or this state psi uh, on space C to Charlie. And the way they can do this is, of course, she could physically just send the register, that would be fine. But here, what we're trying to say is that if A and B are entangled, then Alice can send the state to Charlie without ever sending any quantum information. Okay. So how does that work? So it works as follows. So register C is here, and A and B are here, and we're going to assume that this is in the state pi plus. Okay, so I'm using the convention that pi plus minus is just the state 0, 0, plus minus 1, 1 by root 2, and psi plus minus is the state 0, 0, sorry, 0, 1, plus minus 1, 0 by root 2. Okay. So in the beginning, the state is pi plus, and say the initial state psi here on Charlie's side is say, given by alpha 0 plus beta 1. Okay, and so Alice applies a controlled not and a hard command. Okay, this essentially corresponds to measuring the register CA in the Bell basis, because it's not difficult to check that this converts a Bell state, so a Bell state into an index for the Bell state. Okay, so this is what is happening, and the mathematics. And then she sends this classical information to Charlie, who can, using this classical information, apply some corrections to the state, the register that she's holding, and recover the quantum state psi on her side. Okay, M1. And so that is the circuit, and yeah, it's not very hard to see that this works. The way we see it is basically noting the following. So we note that if you have the state size C, one can write it as, so first of all, one can write the state CA as a combination of Bell states, right? So you can write it as, because we're going to make a measurement so this is the Bell measurement, right? So we just write it in the Bell basis, so then we'll know when you make the measurement what outcome you get. Okay, so what we're going to do is we're going to start with 5 plus 5 prime. Okay, and for 1, 1, it would be the same thing, but minus here. Then for 0, 1, CA, get this CA, this would be 1, 2. 0, 0, plus minus 1, 1. Oh, shoot. Sorry. Here we want to write psi plus psi minus acting on CA, right? And now we're going to use for 1, 0, going to be the same thing except for the minus sign, right? So these are the states that we get. So basically you can rewrite the initial state. So one can write, so that's the key observation, that you can write psi C with, phi plus in AB as the following. So you can write it as half of phi plus 1 CA tensor with alpha 0 B plus beta 1 B. Okay, so if Alice makes a measurement and she gets the outcome corresponding to phi plus on those two registers, then then Charlie already has the correct state on register B. If the state is phi minus, then the state on Bob's part is alpha 0 B minus beta 1 B. Then if it's phi plus, CA, then the state is alpha 1 plus beta 0. And if it's psi minus, then the state is alpha 1, I guess, yeah, minus beta 0. Okay, so depending on which one she gets, she can apply the phase or the x, and she can figure out the state. So that's this is teleportation. So that's an example of an interesting quantum circuit. Yeah, it tells you how to send a state. Okay, good. Now what are we going to look at? We're going to look at yeah, so I promised I'll tell you what I meant by being epsilon close. Let's do that as well. So we have to look at, it's instructive to look at the notion of distances between quantum states and channels. So we'll do that as well. So section distances between states and channels. Okay, so first look at norms. So for an operator O, which is a linear operator from x to y, right? There's already the induced norm. There's the operator norm or the induced norm, which is induced by the underlying Hilbert space, the vector space. So here this is just the max of O acting on psi, such that the norm of the vector, right? Such that psi belongs to x and psi is normalized at most one. Okay. So you're doing max over, yeah, so you just take the maximum of this maximum element in this set. The other one is called the trace norm, which is also widely used. The trace norm says what? So it's defined as, we use this notation, and it's defined as trace of square root or whatever. Okay. And later we'll see that these norms are dual, right? So it would be useful to have this fact that operator norm and trace norm are dual to each other. Dual norms. So what that means is that one can write the norm O as the maximization over O, O, right? So this is just the inner product and trace, where O prime is a linear operator, and the one norm is at most one. Yes, you take the inner product of O with one norm at most. Sorry, inner product of O with O prime, where O prime has one norm at most one, and you maximize that. This will give you uh, the operator norm, and the other way. So if you take the trace, the one norm, this would just be the same thing, except that now we require that O prime has uh, O prime has operator norm at most one. Okay, so this is a fact from linear algebra. Few other things that we would need. Here, so the states. Okay, so theorem 69 is the operational meaning of trace distance. States. Yeah, what is it? It basically says the following. It holds that the maximization of P0 goes 0 plus I actually did not introduce this inner product notation, but it's just, you do trace. The notation I think is just if you have AB in a product, I think it's just trace A dagger B, or maybe the dagger is the other way. I don't remember, but yeah, it shouldn't make a difference here because we're looking at emission matrices. Okay, so P0 row 0 and P0, oh sorry, P1 row 1. So what is the thing that, your outcome was 0, the probability that you got the correct answer, so it's trying to distinguish between row 0 and row 1. So you use two POVMs. So 0 corresponds to declaring the outcome was row 0, or the state was row 0, and 1 corresponds to declaring that the state was row 1. So this is the probability of success, right? And you're allowed to use whichever POVM you want to make the distinction. Okay. So this distinguishing probability, success probability at distinguishing, is at most half and 1/4 of the trace distance between row 0 and row 1. Okay. And so in view of this, we can write a definition. 70, so sigma is an epsilon approximation of rho if for rho sig 1 norm, the face norm is at most epsilon. Okay. Okay, good. Very well. Now we come to fidelity. So fidelity between rho and sigma is given by this expression. So rho sigma is at most trace of square root rho sigma rho, okay, which is essentially just a one norm of root rho root sigma. Okay, so that's just the definition, and it looks a little bit asymmetric, but the nice thing is that if you look at this expression here, um, this is so the trace norm is basically just summing the singular values, if you like, right? Because it's just taking the mode. And because it's just summing the singular values, it's easy to see that you know that f rho sigma would be the same as f sigma rho, because um, root rho root sigma and the conjugate, which is root sigma root rho, which equals root rho root sigma dagger, have the same singular values. Okay. All right. The other note here is that if say sigma is pure, right? So if sigma is psi psi, then f of rho sigma becomes psi rho psi. This just becomes the overlap with the square root. Okay, good. There's an ICF that says the following. So theorem 72 is again called Ullmann's theorem. But this is, for characterizes, so it's an alternate characterization of fidelity. That shows that, so it holds that f rho sigma is the same as maximization over and phi on psi phi, where psi and phi are purifications. So sigma respectively. Okay. Nice. And now we have the following proposition, which relates the, okay, so we have fidelity and trace distance are both used for looking at the notion of closeness for states. Okay, so proposition 73 gives us a relation between fidelity and trace. This is also called the Fuchs Van de graph. And it's the same Van de graph as the Van de graph generator. So Fuchs Van de graph inequalities say what? They say that the following holds. So 1 minus f. So sigma is at most half the trace distance between rho minus sigma, right? And this minus f rho sigma square. Okay, so that's the relation between fidelity and trace distance for all rho sigma. Okay. density matrices. Okay, good. So this is all that I wanted to say about the norms and distances. So all I wanted to say about distances for states. Now let's look at the notion of distances for channels. Um, and this will also clarify the epsilon proximate that we had mentioned when we were looking at um, what were we looking at? We were looking at the, uh, the universality theorem, yeah, saying that all unitaries can be approximated to exponential precision with Pauli-Mini gates if n and m are fixed. Okay, so the notation here is the following. Okay, so we're going to use CXY to denote CPTP channels, so completely positive trace preserving channel or maps, whatever. Okay, and then we'll use TXY when it's, it may not be, linear maps that do not necessarily satisfy, so don't satisfy CPTP. Okay, so we can now define the diamond norm. Is, if you like, okay, so the diamond norm is defined as follows. So given an operator from this TXY, diamond norm, which is written using this diamond, is the same as, or sorry, is defined as the max over delta and said with, so you extend delta with some identity on an extended space W. You look at the one norm. And here you look at X can be any linear operator on this extended space, tensored with X, the initial space, and the norm of X, the chase norm is 1 at most. Okay, and what do we know about W? So W is any Hilbert space at least as large as X. Okay, so beyond that, the value of the norm doesn't change. Okay, and yeah, so basically the physical interpretation of this diamond norm is analogous actually to this one, right? It says that no physical process can distinguish them. So we're going to do the same thing. We'll say that uh, given the channel, there's no physical process that distinguishes them with probability more than what we've written here. The proposition 75 says that no physical process can distinguish two channels, P0, P1, belonging to the set of channels with bias greater than half times the diamond norm. and one of them is given with equal probability half. Yeah. And really what we have is different from 76, which says that uh, channel E1 is an epsilon approximation of E0 if the diamond norm between them is epsilon epsilon. Okay, and so this is what we meant when we said that the in the universality statement that the quantum circuit epsilon approximates the initial channel. That's it. And then the last thing I wanted to tell you was a problem that gives uh, Simon's problem basically. I just wanted to tell you this. I'll do it in just a second.